Hello friends, welcome to Knowledge Galaxy to rediscover the basics with Mayank Tiwari, a premier coaching and training channel dedicated to metallurgy studies and consultancy. Established to cater the needs of students, degree, diploma and AM/IIM metallurgy, competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals and whosoever seeking knowledge and information about various subjects and topics of metallurgy, ferroalloys, operational process optimization, productivity improvement analysis, etc. To impart practical industrial knowledge as per your specific requirements via tailor-made training sessions for your colleagues, employees and students, please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +919907144101 for scheduling and organizing the sessions at your place or via video conferencing. My dear friends, nowadays technology has improved so much that actual physical distance doesn't matter anymore. You can get all your doubts cleared by sitting at your home, at your comfort zone, just by contacting me over WhatsApp or phone, so that for your benefit, please do contact me for any of your doubts. My dear friends, I have made so many videos which are available on my YouTube channel. So I request you to visit my channel regularly and repeatedly and watch all the videos available there, so that you can gain maximum knowledge about the subject and topics, and also request you to watch all my videos from start to finish, so that you can gain the maximum and complete knowledge about the topic. My dear friends, as you know that training is costly, but not to train is still costlier. And when you are not having complete knowledge or don't get any information about the topic which you need to know, so you can contact me. If you don't find anyone who can help you to clear your doubts, you do contact me as soon as possible. And so right now in this video I am discussing about extraction of silicomanganese from marine and low-grade mineral resources. My dear friends, this is the title of my present presentation. As you all are aware that the high-grade manganese ores deposits are very less available and they are also very costly. So whole world is looking for the usage of low grade and other mineral resources which can give substantial amount of grade of ferroalloys with standard grade. So I hope this presentation will help you all to know about how to utilize the low grade mineral resources which are available in plenty, and what can be the procedure and what can be the expected grade. And before going through this presentation, I would like to request all of you to go through the message given in the next video. Next slides. seen and observed in the video that no water can be filled in the pot if the pot is not aseptic, and also if the pot is already filled. The water can only be filled when there is some space in the pot. So, my dear friends, I request you to keep your minds open for receiving the information so that you can receive the information correctly and gain the knowledge. But if you feel that you are already having much knowledge or more knowledge, or if you are not receptive towards receiving the new knowledge or information, you cannot gain anything. So for gaining new knowledge and information, please keep your mind open and be receptive for the new knowledges always. My dear friend, I am having one of very important announcement for you all. The information which I want to share is that if you want to advertise your products, services, company or anything else on my channel, then please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 for putting your advertisements in my forthcoming videos. My dear friends, as you all are aware that advertising in the YouTube channels is very common and very fruitful method of approaching to the mass volume of viewers. So you can contact me for putting your advertisements in my forthcoming videos. Okay, I hope my messages given in the previous slides and videos is very much clear to you all. So now let's start with the synopsis of this presentation. Manganese nodule available in ocean beds is a potential resource of the future for copper, nickel and cobalt. Recovering only these metals containing less than 3% by weight will result in the generation of large amount of residue. In addition to the material losses, several environmental and ecological problems arise out of this residue. The present study has been aimed at reducing the environmental and ecological problems associated with massive generation of this residue together with the utilization of the resources. Presence of equivalent to 20% manganese and equivalent to 16% silicon in the residue has prompted to check its suitability as a raw material for silicomanganese production. Lower manganese content and lower Mn/Fe ratio of the residue than that required for silicomanganese production has been corrected in this study by suitable blending. The efficacy of blending and its thermodynamic aspects using FactSage software are discussed. The studies conducted indicate viability of bulk utilization of the residue through silicomanganese production and thereby reducing the burden on environment to a great extent. So now let's have the introduction. This was the synopsis. Now let's have the introduction. Rapid depletion of major non-ferrous metal resources have stimulated efficient use of available land-based resources and vigorous search for new sources. Manganese nodules available in the beds of Pacific, Atlantic and Indian Oceans appear to be a solution for copper, nickel and cobalt. Concentrations of these metals are comparable to the sum of the land-based resources. Availability of these metals in the ocean beds in manganese nodules is much more than that in the terrestrial resources. Generally, these nodules contain a little over 2% of copper, nickel and cobalt together and equivalent to 10% iron, 20% manganese and around 18% silica. So far, the attempts have been to extract copper, nickel and cobalt from these nodules due to first strategic reasons and second their fast dwindling deposits. Though manganese is the major element in the Osine nodules, little attempt has been made on its extraction owing to its extensive terrestrial deposits. For process focused only on copper, nickel and cobalt, which constitutes less than 3% of the nodules, large amount of residue is inevitable. This would be quite undesirable from the material conservation and process economics point of view. Besides, the environmental and ecological problems associated with this residue are also of great concern. Utilization of this residue for value-added products would be a better option to address the concerns mentioned above. Use of these residues as catalysts and or as an adsorbent for some of the heavy toxic elements is notable among them, though their consumption in these applications will be meager compared to their expected generation. The main problem of the residue and many other low manganese resources has been their low and hence unfavorable Mn by Fe ratio, that is equivalent to 2 by 1 for production of the manganese alloys. This drawback has been overcome suitably and has yielded standard grade silicomanganese. My dear friends, just to interrupt you all, here I would like to emphasize on some special important aspect of Knowledge Galaxy. Here specialized subject-wise coaching classes and topic-wise doubts clearing are available. I am available for all of you to clear all your doubts, and especially for Diploma Engineering, Metallurgy and Mechanical students, Indian Institute of Metals, that is IIM, Part 1 and Part 2, and competitive and recruitment exams for GATE, SAIL and various other government and private sector companies, metallurgical industries, working and aspiring professionals. Here I would like to emphasize that whatever queries and doubts you are having in your mind regarding any subject or topic of metallurgy or any other ferroalloys production, operation, maintenance, so you can contact me for getting your doubts cleared. I will try to provide you accurate knowledge and to the best possible extent at the very shortest period of time, so that you can gain your knowledge, clear all your doubts, so that you can grow in your career, whether it is academic career, whether it is of professional career, and so that you can develop and grow. So to continue with, here complete syllabus coverage for the students aspiring to appear in the forthcoming semester exams, that is December or June, I will be providing you all. So please contact me on knowledgegalaxy26@gmail.com or WhatsApp me on +91 99 071 44 101 for scheduling and organizing the classes or getting informations to clear your doubts via video conferencing, call or WhatsApp. My dear friends, you might have encountered that you might have been having many of the doubts regarding process, technology,
why they are doing, why it is done, how it is done. So, and if you don't find any answer to them and nobody is there to guide you properly, so my dear friends, I am here available to guide you all, to make you know and grow, and so that you don't have any doubts related to your process, products, technology, syllabus, and I will make sure that all of your doubts get clarified and you know the topic and subject very well and completely. So again, let's move on.
The presentation contains a brief theoretical analysis of silicomanganese production to determine the product composition using metal, slag and gas, and a comparison of the effectiveness of two blending materials using high-grade manganese ore and ferromanganese slag. My dear friends, as you already know that the dedicated video on production of ferromanganese and production of silicomanganese is already available in my YouTube channel, and many other related topics are also available in my channel. So please go through my playlist and discover and explore all the videos available in the list, and also go through each video very thoroughly so that you can gain the complete information and knowledge about that particular topic. There is little information other than that mentioned earlier available in the literature on the utilization of the leach residue in silicomanganese production. Generally, silicomanganese is produced in electric arc furnace by carbothermic reduction of manganese oxides and quartz or other silica resources. Out of the large number of reactions taking place during the process, reduction of MnO and SiO2 even below are the vital ones. So first reaction is MnO plus C, this gives Mn alloy plus CO gas. SiO2 in liquid phase plus 2C, this gives Si liquid plus 2CO gas. These are the two main reactions generalized way. These two oxides are much more stable than other oxides normally encountered in manganese alloys production, and hence need higher temperature and lower oxidation potential for their reduction to metallic state. Higher oxides of manganese are reduced to MnO by topochemical reactions at lower temperatures, and hence it appears that the nature of the manganese phase would not matter much. For ores containing silicates, lime has been added to increase the activity of MnO. Being less stable, iron oxides get reduced progressively to its metallic state before the reduction of MnO and SiO2, and as a result, practically all iron reports to the alloy phase. As a result, selective reduction of manganese cannot be attained through maneuvering of the operating parameters, and this restricts the use of resources with low Mn by Fe ratios. My dear friends, in practical industries operations, you might have faced this difficulty that low Mn by Fe ratio ores are not used very much, and it is very difficult to utilize them, and you might have been asked about the reasons for this, that why low Mn by Fe ratio ores cannot be used, or what is the drawback of using low Mn by Fe ratio ores. So I hope I have given and provided you the reason why low Mn by Fe ratio ores are not utilized or cannot be used. It is very difficult to utilize low Mn by Fe ratio ores. So I hope I have provided you the reason and answer. Further, the requirements of higher manganese reduction or recoveries are contrasting to that of silicon, a basic slag for manganese and an acidic slag for silicon reduction. I again repeating it. Further, the requirements of higher manganese reduction or recoveries are contrasting to that of silicon, that is, a basic slag is required for manganese reduction and an acidic slag for silicon reduction. Composition of the charge and the operating conditions hence need to be balanced to have good recovery and desired grade. In manganese alloy smelting, activity of manganese 2 oxides has been reported to be critical in getting good recovery of manganese. Reports suggest that secondary raw materials such as slag, etc. in the charge may affect the recovery of manganese adversely. Here the slag refers to high carbon ferromanganese slag. Partial replacement of lime by MgO increases the melting temperature as a result of the increase in resistivity, which in turn enhances the grade and recovery in silicomanganese alloy production. My dear friends, this is the main reason which it depicts why to use dolomite, which is a double oxide of CO and MgO, as a flux in place of lime. So this is very useful point. Please do remember this. It is reported that silicon in combination with carbon is a better reductant in manganese alloys smelting than silicon alone. Quartzite coke has been found to be better in terms of recovery and grade of manganese than metallurgical coke. Silicothermic reduction of slag has also been tried for the production of silicomanganese. In silicomanganese process, the manganese reduction is slower and corresponds to the second stage described by Skjæveland and Olsen. The slow reduction rate in silicomanganese process is also attributed to the decreased MnO activity due to the presence of Al2O3 and or SiO2. Molten iron dissolves manganese and reduces the activity of manganese, and this drives the reduction of MnO to maintain the MnO by Mn ratio required for the prevailing condition. With the increase in silicon content of the alloy, carbides become less stable and silicides becomes dominant, which imply the carbon content of the alloy decreases with increase in silicon content. My dear friend, this is also a very good and very important observation, that because silicon and carbon, they are inversely proportional. That means with the increase of silicon content, carbon content decreases, and as you might have observed that higher grade of silicon in silicomanganese has a lower amount of carbon, and this is also depicted by a very good, very nicely explained curve, which is also available in my videos of production of silicomanganese. So you can refer to that video for knowing about the curve. Low manganese, high iron ores can also be used for making silicomanganese after converting it to a high manganese slag. it is possible to obtain silicomanganese with low sulfur and phosphorus content even from fine substandard manganese bearing materials using plasma technology. The escape of SiO and manganese vapors, etc., which are likely in silicomanganese smelting, needs to be minimized suitably to avoid material losses. Now let us have some theoretical considerations. Thermochemical computations are conducted using FactSage on a typical charge used in the experiments. FactSage is an application software for calculation of phase equilibria in multi-component, multi-phase, non-ideal systems. It works by Gibbs energy minimization using diverse set of solution models available within it. A wide range of chemical, environmental, metallurgical and geological systems can be analyzed with this software. The moles input to the software is given in table 1 in next slide and corresponds to the charge given at table 8. Table 8 is presented later in this presentation. Composition of slag and alloy, that is silicomanganese, has been determined using the software and compared with that of the experimental values. Gas compositions could not be compared as it is not available. So this is the table 1 which shows the charge composition in moles used in FactSage analysis. You can pause the video and observe the table contents. Okay, moving ahead. So now let us discuss the experimental, what we have done. So first is materials and methods. C nodule residue obtained after recovering the copper, nickel and cobalt through SO2 ammonia leach process is the main raw material. The chemical analysis of a representative leach residue sample used for the present study is given in table 2. So this is the table 2 which shows chemical analysis of C nodule residue. As usual, you can pause the video and observe the table contents. Okay. Though manganese is the major element in the C nodule or C nodule residue, its manganese content is considerably lower than that are being used in ferroalloy industry. Besides, the Mn by Fe ratio of the residue is considerably lower than that required for a standard grade silicomanganese. As the scope of improving the grade of the residue by physical concentration methods is practically nil, the residue has been enriched through proper blending. A high-grade manganese ore or a ferromanganese slag has been employed for this purpose, that is for the blending of low-grade manganese C nodule residue. Ferromanganese slag used has been obtained from one of the ferromanganese producers. The manganese ore has been from indigenous mines. Table 3, which is given in the next slide, gives the chemical analysis of the ferromanganese slag and manganese ore used in the experiments. Ore contained more than 40% manganese, whereas the slag has the advantage of very low iron and phosphorus content, most of which have been removed during the ferromanganese production. A low ash coke was used as a reducing agent. It had fixed carbon content that is Fc of around 85% and about 12% ash. Various fluxes used in the experiments such as quartzite, foundry sand having 98% silica, calcium fluoride, lime, etc. were of industrial grade. So this is the table 3 which shows the chemical analysis of ferromanganese slag and manganese ore. Compositions of various raw materials such as leach residue, ferromanganese slag, etc. was determined by standard analytical methods. Depending on the concentrations of the elements, weight, chemical or atomic absorption spectrometer, that is AAS, was used for analyzing. Particle size distribution has been measured using Ishimatsu SA-CP3 particle size analyzer. So now let us discuss about the smelting process. The fine nature of the residue characterized by star D50 of equivalent to 10 micron and D10 of equivalent to 3 micron was necessitate its agglomeration to avoid material losses and to have sufficient charge permeability. The C nodule residue was pelletized in a drum pelletizer of 0.31 meter diameter with 2% bentonite as binder to get pellets of 6 to 8 mm size. The green pellets had a crushing strength of 200 to 250 gram and drop strength of about 5 to 7 drops. Pellets were dried suitably in an oven before being charged into the smelting furnace. Here star dx is equal to y micron, means x% of the particle is below y micron. A single electrode DC arc furnace was used for smelting experiments. The experimental setup is shown in figure in the next slide. Consists of a graphite electrode, a graphite crucible and a thick graphite plate. The graphite electrode is connected to the positive of the power source. The graphite crucible rests on the graphite plate which is connected to the negative of the power source. So this is the experimental setup for smelting and details just I have explained. The crucible and the plate together act as the negative electrode of the system. The graphite electrode which is connected to the positive of power source can be positioned at any desired level in the vertical direction with the help of a motorized rack and pinion arrangement. A refractory jacket capped around the crucible prevented the heat losses from the system. The charge is smelted in the graphite crucible. Small amounts of charge consisting of residue pellets, manganese ore and or ferromanganese slag, coke and fluxes were added to the arc zone in the crucible. As mentioned earlier, manganese ore and ferromanganese slag are used to enrich manganese and hence to correct the low Mn by Fe ratio. As smelting proceeded, further charge addition was made to the crucible. Each of the smelting experiment used about 4 to 5 kg of charged material. A soaking time of about 40 minutes after the complete charge addition at the desired temperature was given to ensure maximum reduction of MnO and SiO2 and proper slag metal separation. Then the metal and slag were allowed to cool in the crucible and were separated weighed and analyzed for determining the grade and recovery. So now we have come to results and having some more discussions. Due to the very fine nature of the residue and lack of crystallinity, no sharp peaks were seen in the X-ray diffractogram. However, presence of Mn2O3, MnO.Mn2O3, Mn3O4, Fe3O4, FeO and SiO2 phases are likely in the residue. Thermochemical analysis. Let us discuss about the thermochemical analysis of the experiment. Thermochemical analysis of a laboratory scale experiment containing leach residue and ferromanganese slag, which is given in table 8 in the chart, have been done. The results of thermochemical analysis using fat sage are given in tables 4 to 6. Table 4 contains the composition of the output streams at various temperatures from 1673 to 1973 Kelvin for the input given in table 1. From table 4, it is observed that the MnO content of the slag decreases with increase in temperature. This is quite expected. I hope I don't have to explain it much. So this is the table 4, which gives the compositions of the fat sage output. As usual, you can pause the video and observe the content of the table very carefully. As the temperature increases, more MnO gets reduced from the slag phase, most of which reports to the alloy phase, and the remaining escapes to the atmosphere as vapor. The silica content of the slag, however, shows an increase, reaches a maximum at 1823 Kelvin and then declines. On the other hand, the CaO plus MnO divided by SiO2 plus Al2O3 ratio, which is given in table 4, decreases till 1823 Kelvin and then increases. These two together shows that the manganese reduction predominates till 1823 Kelvin and silica reduction accelerates after 1823 Kelvin. Iron content, that is weight percent of the alloy phase, decreased with temperature, though it remains same in absolute terms, that is number of moles. The relative decrease is due to the increase in manganese and silicon entering the alloy phase at higher temperatures. Manganese and silicon in the alloy phase increases with the temperature and can be attributed to the decreased stability of their oxides at higher temperatures. The rate of increase of silicon reduction is less when compared to that of the manganese. Table 5 contains the mole fractions or partial pressures of vapor and gases emanating from the furnace at various temperatures. It is observed that there is increased loss of manganese and silicon with temperature. So this is the table 5, which shows the composition in mole fractions of gas phase in fat sage. Table 6 depicts the percentage loss of manganese and silicon as vapor with increase in temperature. It can be seen that beyond 1873 Kelvin, the incremental quantity of manganese reporting to the alloy phase is insignificant. It mainly contributes to the vapor phase only. But to have the required silicon content, one has to be above this temperature. Hence, a proper balance has to be arrived to have the required silicon content without much loss of manganese. Thermodynamic calculations shows some amount of solid silicon carbide formation at elevated temperatures which may pose operational difficulties. So this is the table 6 which shows the loss in weight percentage of manganese and silicon with temperature in gas phase. Okay, so far so good. Now let us move on and discuss about the smelting of leach residue. Due to the low manganese content and Mn by Fe ratio of the residue, a medium grade silicomanganese alloy listing silicon 16%, manganese 63% with silicon 14 to 7% and manganese 60 to 65% range has been aimed. The leach residue was smelted as mentioned above. The results of the experiments using manganese ore as the blending material are shown in table 7, which is given in the next slide. The grade of the alloy obtained was marginally lower than envisaged as far as manganese and silicon were concerned. However, good recovery of manganese and silicon has been achieved. So this is the table 7 which shows the results of smelting studies for blending with manganese ore. So this is the result. So you can observe the video and pause the video and observe the contents. As is depicted in the above table, that the low grade of the alloy is due to the high iron content of the charge, most of which is reporting to the alloy under the experimental conditions used in the present study. Increasing the percentage of manganese ore in the charge will help in increasing the Mn by Fe ratio content of the charge, which in turn lead to a grade conforming to standard specification. Since our main aim was to utilize the residue, experiments with increased manganese ore in the charge has not been attempted. An alternative material has been tried instead to enrich the manganese content, and the details are given in the next paragraph or next slides. The problem can also be overcome by removing most of the iron from the charge by a first stage smelting, wherein most of the MnO are kept unreduced in the slag through proper maneuvering of the operating parameters. The slag thus obtained will not only be rich but also have high Mn by Fe ratio required in the ferroalloy manufacture, which on further smelting with additional coke ensures silicomanganese of desired grade. Ferromanganese slag, the alternative enriching material used, contains practically no iron, that is depicted in table 3 analysis, as most of the iron and phosphorus were removed during the ferromanganese production. This has helped in keeping the iron input to the furnace same as that in the residue. The parameters studied included effect of holding time, silica addition, etc. The results are given in table 8, which is shown in the next slide. In general, the slag formed in the experiments with ferromanganese slag addition was viscous and as a result caused foaming and poor slag metal separation. It is seen that the manganese content of the alloy equivalent to 60% was within the desired level. So this is the table 8 which shows the results of smelting studies for ferromanganese slag addition as enrichment. The silicon content of the metal has also been brought to the desired level with ferromanganese slag blending. However, the manganese recovery was around 50% only, and this may be attributed to metal entrapment due to increased viscosity of the slag. The low iron recovery substantiates this argument. Low grade and secondary nature of the charged materials like leach residue, ferromanganese slag, etc. may also be responsible for the low recoveries as reported in the literature. Low activity of MnO of the charged materials as reported by Tolstoguzov can also lead to reduced recovery. It can be seen that the results more or less match with the grade obtained through thermochemical simulation using FactSage. Evaluation of the results on the basis of the alloy grade obtained shows that ferromanganese slag is apt for blending the C-nodule residue. The very low iron content of the slag ensured minimum iron input to the charge, which helped in maintaining the iron content of the alloy as minimum as possible and thereby pushing the manganese percentage to the higher side. Ferromanganese slag, being a byproduct of ferromanganese production, has little phosphorus content compared to that of manganese ore used. As a result, phosphorus content of the silicomanganese alloy produced was around 0.15% and is well within the stipulated limit of 0.3% max for a standard alloy. Carbon content of the alloy decreased with increase in silicon content of the alloy as described in the literature and as I have mentioned already previously. However, the low recovery needs to be improved and may be possible by a proper charge optimization, that is of residue, slag and ore compositions, etc. So now, so far so good. Now we have come to the conclusions. To sum up all the discussions what we have done, what I have presented in this presentation. So let's have the conclusions. Theoretical studies have shown that manganese and silicon reduction enhanced with temperature, though a part is lost as manganese vapor and SiO gas respectively. Beyond 1873 Kelvin, manganese content in absolute terms remains same. Beyond this temperature, whatever extra manganese gets reduced mainly contributes to the vapor phase and hence is lost. The requirements of the silicon and manganese reductions are contrasting and need proper tuning to have efficient operation. I am again repeating this as it is very important observation. The requirements of the silicon and manganese reductions are contrasting and needs proper tuning to have efficient operation. Though good recoveries have been obtained with manganese ore, higher iron content of the charge diluted the product grade in terms of silicon and manganese. Increasing the manganese content alone is not sufficient to obtain a standard grade, that is of silicon 16, manganese 63 grade silicomanganese. So these are all the main conclusions of whatever observations and experiments I have explained. And moving ahead, some more conclusions. it is imperative to have a charge with a high Mn by Fe ratio as well as high manganese content. With ferromanganese slag alloy with desired grade could be achieved and matches more or less with that obtained by thermochemical analysis. I again repeat this. I am again repeating this. With ferromanganese slag, alloy with desired grade could be achieved and matches more or less with that obtained by thermochemical analysis. When ferromanganese slag was used, the recovery of manganese and silicon was low. This is mainly due to metal entrapment in slag and high slag by metal ratio. Blending the C nodule residue with a suitable combination of ferromanganese slag and manganese ore will help in improving the recovery of metals. Alternatively, a two-stage smelting of residue may be adopted which correct the Mn by Fe ratio without blending. The same process may be extended to other land-based ore finds available in plenty but remains unutilized due to their low grade. My dear friends, here I hope I have covered every aspect of using low grade resources of manganese ores. So, dear friends, I am providing you all the informations free of cost which are available in my YouTube channel. So, do help me by watching all my videos. Do subscribe my channel. Regularly visit and repeatedly visit my channel. Do watch all my videos, contents, like the content, share with your friends, and so that I also get motivated from each one of you as you subscribe to my channel. I am very much thankful to all my subscribers who believe in me, have subscribed my channel and like my content. So to motivate me further, please do subscribe my channel, increase the subscriber count, share with your friends so that others can also gain the knowledge. And my dear friends, all if you subscribe my channel, this will motivate me to do further better. So I hope you like the content and found the video worth. So again request you to please don't forget to like, share and subscribe the channel. Also remember to press the bell icon so that you can get the notification of the new videos promptly. My dear friends, here if you want to advertise about your product, services or company or anything else for gaining popularity in my channel, so you can contact me so that I can put your content for advertisement in my videos, forthcoming videos. So it will be a good platform to advertise. So do contact me as soon as possible. Thank you very much for watching this video till the end, and I am very much again thankful to all of you who helped me, who believe in me, and please do visit my channel regularly and repeatedly. Thank you very much again. See you in the next video. Thank you.